All right, we are moving into chapter 3, and the first section here is 3.1, exponential functions and their graphs. So, just a little definition here. Exponential functions are anything a to the x, and we want to talk about, at least for now, a being positive, and we don't want to have a to the first because, a does not equal 1 because 1 to anything, 1 to the 5th, or 1 to the 10th, or 1 to the 1,000,000th is just 1. And so that's not very exciting when we have the graph where y is always equal to 1. So we do not want to have a being 1. So let a be any other number than that, and we're going to be in business, and x is real. No imaginary functions going on here. So when we put them all together, exponential and logarithmic functions, the two different things we're going to be looking at in chapter 3, these are called the transcendental functions. Say that 10 times fast. Transcendental. So we're going to move through a couple early examples here because I think you're going to be just fine doing these. Example 1 in the book just reminds you how to put this into your calculator. So if we have 2 to the negative 3.1, how would we put that in our calculator? Here's your keystrokes and your answer right here, 0.1166291. So go ahead, you can try that, put that in your calculator, make sure it works, but I think everybody should be pretty much up to speed on entering exponentials into their calculator. So knowing that, we can start to graph some exponential functions. And so exponentials are going to be taking off. They start close to the axis, pick up speed, and then get straight up towards vertical pretty quickly. So we have two graphs here, y equals 2 to the x and y equals 4 to the x, and you see both graphs over here with 2 to the x and 4 to the x. And if you plot these on a t-table here, you'll see that the graphs start as pretty small fractions, but pretty quickly grow to be big numbers. So that's why we call them exponential. They're getting exponentially bigger because the graph is some constant to an exponent. All right, so this is pretty standard. If we're going to do a t-table, go from -3 up until 2, or even add in an extra column with 3. And that should be plenty of points for you to graph your exponential function. Looking at something similar here on example 3, we're going to have a negative exponent, negative 4 to the x, and 4 to the negative x, and 2 to the negative x. And so the graphs are going to look exactly the same as 2 to the x and 4 to the x, but they're flipped horizontally. So they're flipped. This was y equals 4 to the x, looks like this. Y equals 4 to the negative x, looks like that. So we'll flip things around. All right, which brings us to the first problem I would like you to try. We're going to use the 1-to-1 property. And what we're saying here is that if we can get our base to be the same, then our powers are going to equal each other. So if we take a look at this first equation here, 9 equals 3 to the x plus 1. We need the bases to be the same. So we can realize that 9 is equal to 3 squared. And at that point, our bases 3 and 3 can cancel out. And we're left with just the powers. 2 equals x plus 1, and from there we can solve. Same thing on example B. 1/2 is the same as 2 to the negative 1. 8 is the same as 2 cubed. And as soon as we have that, we can cancel our bases and get negative x equals 3, or x equals -3. So here's the first one I'd like you to try. I'd like you to try problem 51. Please pause the video, try this problem, and press play when you're ready for the solution. All right, if you're here, I'm assuming you're ready to go. Let's get our bases the same. The common base here is going to be 3. 27 is 3 cubed. As soon as we have that, we can cancel our bases and set our powers equally to each other. And so x will equal 2. We can always go back into our original equation and check this. Say 3, plug in 2 for x, and see what we get. 2 plus 1 is 3, so we'll have 3 cubed, and 3 cubed is 27. And so we have checked to make sure that we are correct.